From now on, we're going to talk about some strategies for optimization. First of all, when we train our networks or our AI models, we need to monitor the training process. And if there are something wrong in the middle, then we need to take some actions. And when we're monitoring the training process, we basically log the train loss and validation loss. And by looking at how train loss and validation loss evolve, we can interpret those evolution and get some intuition how the training process is going. And in this case, in this example, the training loss and validation loss is quite different. And another thing is they both do not decrease. In this case, we say underfitting has occurred, which means our model does not have enough capacity to decrease losses. In other words, our train data or target data entails very complicated distribution. However, our model capacity is not enough to model this complexity. In this case, we need to employ more complicated or models with more capacity so that we can model this complicated distribution of the trained data. And if this occurs, both train and validation loss decreases. However, as you can see from here, they can go down further. And we say the model has not converged yet. The model can be trained longer. So we can take more iterations for training. We should not stop here. And in the previous slides, I mentioned that we keep training until the validation loss decreases, and we stop training when the validation loss does not decrease or increase. So we usually do not run into this situation. And another situation is like this. The train loss decreases, keep decreasing. However, the validation loss remains the same or starts to increase. In this case, we say overfitting is occurring. Train loss decreases, but validation loss increases. In this case, our model is doing very well on our trained data. However, the performance on the validation data is decreasing. And it is like you are doing well on practice problems. However, you are not solving the actual test problems. And what we really want to do is doing well on test, not on practices. So this is a situation we should avoid. And we usually stop training when the validation loss remains the same or it starts to decrease. And this is another case. Both validation loss and train loss remains the same, and they are very low. Both are very low. And this is one of the ideal cases of training. This is what we actually want. The model is doing well on both practices and actual test. And sometimes the validation loss can be noisy like this. In this case, validation set might be too small. Because it is too small, it does not reflect the actual distribution of the data in the world, in the real world. That's why the distribution is noisy. In this case, we might collect some more data for validation set. And this could also happen. In this case, the train loss converges and validation loss also converges. However, there is a big gap between the validation and train loss. This is when validation set is easier than training set. You need to come up with better validation set. And for monitoring the training process, we usually use TensorBoard and other tools as well. And in the later of this course, we're going to have a look at how we can use TensorBoard. And you can visualize various things, training loss, validation loss, and the results of the current model's prediction. We can do various things. And in developing AI models, what we focus on is improving generalization. Because as I mentioned, we want to do very well on test data, not just practice problems. And to improve generalization, there are many vectors we can tackle. In respect of data set, we can augment data and do other things like label smoothing or leveraging unlabeled data or leveraging related data, things like this. We cannot have a look at all of these, but some of them, like data augmentation in this course. And you can also architecturally set your model so that it improves the generalization. And some of them are weight initialization strategies. And you can choose the best activation functions for your application. And you can also come up with residual layers or knowledge distillation. And there are also other techniques that normalizes data or the weights in the middle. And you can also come up with some techniques to somewhat switch or notch the training loop so that it improves the generalization. And we already saw this regularization, L1 and L2 regularization. And we're going to have a look at some of them. And the first topic is data augmentation. What is data augmentation? Let's first discuss the motivation of data augmentation. Deep neural networks must be invariant to a wide variety of input variation. When we search the images for sea otter, you can see various images. Although they are all representing sea otter, they have different backgrounds, different posture, and different colors. However, and we say those variations are large intra-class variation. And we want our deep neural networks to handle all these variations very efficiently and effectively. And the thing is, we cannot collect all these data. And how can we resolve this issue? Here comes data augmentation. Data augmentation is one of the best ways towards better generalization. Actually, the best way towards better generalization is train on more data. If we can collect more data, then that is the best scenario. However, data in practice is often limited. And what we do is create fake data from the existing data. For example, we just have this data. However, by applying some geometric transformation or changing the brightness or contrast, we can come up with some fake data. However, in the process of modifying our original data, we need to preserve the semantics in the data. And even simple operations like translation or adding per pixel noise often already greatly improve generalization. So we don't have to come up with complex data augmentation techniques, but even simple ones already show good performance on improving generalization. And I'm going to show you some examples of data augmentation. And the first one is image cropping. You just crop some of the part by enlarging the image. So you can see here the head of this sea otter is enlarged. So you just enlarge this image and crop some parts. So here you don't see the upper head. However, even though you see this part, you can recognize that this is a picture of sea otter. And our deep neural network will be able to recognize sea otter even given this image. And another example of data augmentation is affine transformation. You can geometrically translate or rotate the images like this. And you can blur the image. In the later of this course, we are going to talk about convolutional neural network. There we are going to discuss what filter for images is. And you can apply a Gaussian filter and the image becomes a little bit blurry. And you can control the blurriness using this sigma. And another thing is Gaussian noise. This one is different from the previous one. In the case of Gaussian blur, we modify the actual pixel values by blurring or modifying the actual pixel values. However, in the case of Gaussian noise, we just add Gaussian noise. So you can see the difference between Gaussian blur and Gaussian noise. We can also control the degree of Gaussian noise by controlling sigma. And you can cut out some parts of the image. And humans can recognize sea otter even though some parts are missing. And we want our models to do the same. And that is what cutout is doing. We cut out random parts from the image. And we can also control the contrast. By modifying the contrast, we can come up with various types of fake images. And we can add some cloud effects. And we can randomly combine all these operations. I just showed you just a little small part of data augmentation techniques, and there are other data augmentation techniques. And you can combine all those techniques randomly. And however, there are some things you need to keep in mind when you're applying data augmentation. When comparing two networks, make sure you use the same augmentation. And you should consider data augmentation as a part of your network design because it could affect the performance of the network. And it is important to specify the right distribution. However, this is done empirically, but not theoretically. You can also come up with the idea of combining the ensemble idea. At training time, you sample random crops scales and train one model. At inference, you just average predictions for a fixed set of crops of the test image. But personally, I don't see this technique that a lot. And there is a technique that is called auto-augment. This uses reinforcement learning to find strategies automatically. It finds what combinations would improve the generalization the most. And nowadays we have deep auto augment, which is an improved version of auto augment. And these techniques try to find the best combination of data augmentation for maximizing the performance. Okay, that was about data augmentation. From now on, we're going to talk about data preprocessing. I showed you that what happens for positive inputs. In this case, if our inputs are only positive but don't have negative values, and when you calculate the gradient with respect to parameter a sub I, this one, you'll first receive the upstream gradient, and then local gradient like this. And if both are positive, then all gradients will have the same sign. And even though we have various choices for our gradient searching space, in our gradient searching space, it doesn't explore these areas, but it only goes through this direction. And that could cause some bias for our network. Therefore, we should preprocess our input data such that it is well distributed. That's the motivation of data preprocessing. And we also saw this when the data distribution is quite different in each dimension, then it's quite hard to perform optimization. However, if we standardize the input data so that both x1 and x2 directions have similar distribution, then the gradients might have similar values in each dimension, and the efficiency of optimization will improve. That's another motivation of data preprocessing. And we use the term covariance shifts. Training assumes, or our model assumes, that the training data are all similarly distributed. And mini batches should have similar distributions. If the mini batches have all different distributions, then AI models will be perplexed. AI models, it is a hard burden for AI models if many batches have different distributions. And we can standardize the distribution by data preprocessing. And each mini batch may have different distribution. That's what happens in practice. And that is called a covariance shift. And this could not just for the input layer, but it could also occur in each layer of the network. And what we want to do is standardize the distribution so that the training process becomes more efficient. What we do is move all batches to a standard location of the space. But where? To determine where to push our data, we'll follow a two-step process. The first step is move all the batches to have a mean of 0 and unit standard deviation. And this process eliminates covariance shifts between batches. So move this batch to the center point, this batch to the center point, again and again. And so this is the first step, moving all the batches to the center point. And after that, what we do is move the entire collection, move the entire batches to a appropriate location. And how do you find this appropriate location? This is done through learning. Our network will automatically learn where to move our batches. Okay, there are two steps for data pre-processing. One is called zero center. We calculate the mean of the data and subtract this mean from all the data. This will be our new data, centered at zero. And normalization means we use the standard deviation or variation and divide the value with the standard deviation. Then it becomes normalized. This is zero-centered data and normalized data. Another thing is we can decorrelate the data. So it is not correlated. So in this case, X1 and X2 have correlation. But in this case, no correlation. And whitening means divide by square root of eigenvalues of covariant matrix. It becomes like this, Gaussian. And by applying data preprocessing techniques, classification loss becomes less sensitive to changes in the weight matrix. And common practices for images is like this. AlexNet came out in 2012, and this one applied this technique, subtracting the mean image. And this mean image is calculated from the training data. It adds up all the training images in an element-wise manner, and then come up with a mean image having the same dimension, W by H by 3. And VGGNet calculated mean image along each channel and subtract per channel mean. So it has only 3 numbers. ResNet calculate per channel mean and per channel standard deviation and conducted denormalization. And whitening is less common. Okay, this is the first question. Stop the video and think about the answer on your own, and let's check the answer together. Okay, let's check the answers together. The answer is the fourth option. When overfitting occurs, we saw this graph, the training loss decreases, but the validation loss starts to increase. After this point, overfitting is happening. And AI models should be invariant to variations in inputs. And this is sometimes referred to as generalization. And pre-processing the input data aids in spreading the distribution of gradients. And that gives a good gradient flow. And data augmentation with simple operations like geometric transformations often lead to generalization improvement. So we don't have to come up with very complicated or complex data augmentation techniques, but even simple operations can improve the performance. However, normalizing the input to the network only affects the first hidden layer. And what about the other hidden layers? This is the question we're going to discuss from now on. To tackle this problem, batch normalization emerged. It came out in 2015. It is a very, very popular and famous technique to normalize or remove covariance shift. So what is batch normalization? Batch normalization normalizes hidden layer inputs, and it helps with exploding or vanishing gradient problem. We saw in the backpropagation class that to calculate the loss according to in respect of a certain parameter, what we do is we apply chain rule and calculate the loss in respect of xi. And what if all these values are less than 1? Then these values, when multiplied multiple times, will converge to 0. And that's what vanishing gradient is about. And what about these values are larger than 1? Then these values will diverge. In that case, we say exploding gradient. However, if we employ batch normalization, then we can increase training stability and convergence rate. We can avoid these kind of situations and can be understood as normalization layers. What I mean by layers is batch normalization entails additional parameters, meaning that we have some parameters that can be trained from data. All right, so let's have a look at this example. Let's say we have a single layer network that looks like this, and the following could lead to tough optimization. Inputs are not centered around 0, then we might need larger bias to cope with the data bias. And inputs X have different scaling per element. We saw this picture, W2, W1. So the loss function or loss space looks like this. In these two cases, optimization becomes very tough. And the idea of batch normalization is force inputs to be nicely scaled at each layer so that the optimization becomes somewhat smoother. And suppose we have net input Z1 at the second layer. So here, Z1 at the second layer is calculated by 2, 1, say 2. W11 times A1 plus W12 times A2 from these first layers. And we do this for all other components. And then W15 second layer times A5 first layer. And after that, after we calculate the net input Z12, we pass this value to an activation function. And this becomes A12. And we saw in the previous sessions, we can abbreviate all these operations using matrix notation. We saw this. And now you might understand what the first component of the second layer is calculated. This one is after applying an activation function to this Z1. And let's say, so we're going to omit the layer index. And what we do when we are doing batch normalization, we first normalize the net inputs. So these are there. In this example, we have Z1, Z2, Z3, Z4 in the case of second layer. In the first layer, we have 5 Z's. Here, what we are doing is we first normalize these. To do that, you first evaluate the mean and the variance. And using these two values, we calculate z prime like this. This is normalization. This is the first step. And what we do next, and in practice, rather than just dividing this subtractive value by the variance or standard deviation, we add a small number here for numerical stability. When this value becomes 0, then this will cause division by 0 error. And to avoid that, we add a small number epsilon here. And the next step is scale this value. You saw in the previous slide that after we normalize like these batches, the center like this, that was the first step done by this process. And after that, what we do is move this group into another position, like here. To do so, we employ gamma and beta. And using these two values, all these batches find new location. And these two values, gamma and beta, are learnable parameters. This is what I meant by we can learn some parameters for batch normalization. And we usually consider batch normalization as a layer because it contains some parameters that are tunable or learnable. Okay, that was the second step. And this beta controls the new mean. And this gamma controls the spread or scale of the new data. So we first normalize the data and then add scale and mean like this. And this is our new value. And technically, a batch norm layer could learn to perform standardization with zero mean and univariance. This could be learned as 0, and this could be 1 after learning. That is also possible. And we just let our network determine which values might be the most optimal one. All right, so that is the process of batch norm. We first feed input, and then the net input is calculated. And then we standardize the net inputs, and then we scale the values, and then we pass this value through an activation function. We get the first hidden layer values, and these first hidden layer values become the next net input for the second layer. And then we do the same process here and here. Another thing to note here is because we have beta here, this parameter makes the bias redundant. Therefore, when we are applying batch norm to our network, we don't have to add bias. Also note that the batch norm parameters are vectors with the same number of elements as the bias vector. And batch norm during inference or interaction, we use exponentially weighted average of mean and variance. Because at training, you can calculate mean and variance from batch. However, during inference, we are dealing with just one sample. Therefore, we cannot calculate mean or variance when we are inferencing. Therefore, we need to come up with a way to provide mean and variance to our network. And there are two options. The first one is when we are inferencing multiple samples, we calculate the exponentially weighted average like this. We saw this in the momentum. We calculate the running mean and running variance. Or the second option is we use global training set mean and variance. By doing so, we just fix the value of mean and variance. And whenever an input comes, we just apply this predefined mean and variance. However, in the first option, we need to evaluate mean and variance every single time we are inferencing for one sample. And batch norm came out to deal with the covariance shift. However, we saw this covariance shift is a jargon for saying that the layer input distribution changes. But there is no guarantee or strong evidence that batch norm helps with covariance shift. However, it definitely improved the performance. Maybe batch norm just provides additional parameters that will help layers to learn a little bit more independently. And there have been numerous research outcomes to interpret the behavior of batch norm, like how does batch normalization help optimization? And okay, in this paper, it turned out that batch norm enables faster convergence because we can use larger learning rate. Therefore, when you're training your network, if you want to use larger learning rate, you better employ batch norm. And this paper claims that the good performance of batch norm seems unrelated to covariance shift prevention. They analyzed this effect. And there are, as I told you, numerous research outcomes to interpret the behavior of batch norm, like this. Okay, and there are variants of batch norm. In our example, we computed the net inputs and then applied batch norm. Then we used our activation function. And this becomes the next input for the next layer. And in this case, the activation function follows after the batch norm. However, you can apply activation function before batch norm. This is called post-activation. This one makes more sense, but less common. Because activation function has its own distribution and its own effect. However, if you apply batch norm after activation function, then it can cancel out the effect of activation function. And there are some benchmarks. What about employing batch norm before or after? You can have a look at this research outcome if you're interested. And practical considerations are like this. Batch norm becomes more stable with larger mini batch sizes. This is straightforward because we are calculating mean and variance. And if we have more samples, then our estimate of mean and variance becomes more accurate. Therefore, we better use larger batch size when we're applying batch norms. In other words, if we cannot afford big batch size, then we should not employ batch norm. And why mini batch sizes as powers of 2? We know this because our computers are usually use power of 2. Okay, this is kind of recap. I told you that we calculate the mean and variance, and this could be per channel mean or per channel variance, and we normalize the data like this. And if zero mean and unit variance might not be the optimal, then we just employ gamma and beta, and this will get modified during the training process. Okay. And estimates of mean and variance depend on mini batch. Therefore, we can't do this at test time. And I told you that during test time, we just use stored mean and variance, or we use running average. I told you this. And another thing is, during test time, batch norm becomes a linear operator. And we can fuse this linear operator with the previous fully connected or convolutional layer. And the last thing I would like to mention regarding batch normalization is how we can do backpropagation. I told you multiple times that we can learn gamma and beta. And to learn these parameters, we need to be able to calculate the gradient in respect of gamma and beta. And if you construct a computation graph for batch normalization, you can derive this gradient in respect of each parameter. And I told you this is also another recap. We usually insert batch norm after fully connected or convolutional layers and before nonlinearity. This is common practice. And batch normalization makes deep neural networks much easier to train because it improves the gradient flow and allows higher learning rate, which results in faster convergence. And networks becomes more robust to initialization because if the distribution is different in each dimension, like this, then the scales for each dimension should be different. However, by employing batch normalization, these dimensions become normalized and having similar distributions, so we can easily initialize the weights of the parameters and acts as regularization during training and zero overhead at test time. Because it becomes a linear operator, we can fuse these batch normalization layers with other convolutional or fully connected layers. And this is important. I am mentioning this multiple times. Batch normalization behaves differently during training and testing. And sometimes this is a very tricky and it becomes a very common source of bugs. And batch normalization for convolutional networks, for fully connected layers, the input looks like this, n samples with the dimensions. And when we calculate the mean and variance, the dimension of mean and variance becomes 1 by d. So does gamma and beta. And we can normalize the input using this equation. And we're going to have a look at what convolution is in the following sessions. And we can also implement spatial batch norm. In this case, the input looks like this, m by c by h by w, because c means RGB channels, and h and w means height and width of the image. And you might know that convolution is related to images. And we have n images, that's all. And when we normalize, we calculate the mean and variance in these directions, n, w, and h. And so do gamma and beta. So we can normalize the input this way. And there is another concept called layer normalization. Batch normalization works for we calculate the mean and variance along the sample dimension. However, layer normalization calculates the mean for each sample. So the dimension becomes n here, and this d becomes 1. So this is the difference. And for gamma and beta, the dimensions are the same. And there is another concept called instance normalization. This is for convolutional networks, and this has the same behavior at training and test. We just calculate the mean and variance for each instance. So here H and W becomes 1. And I'll show you another picture. Batch norm calculates mean and variance in this n direction, and layer normalization this direction. So we are calculating mean and variance for each sample. And group normalization is generalization of batch norm, layer norm, and instance norm. I'm going to show you another picture. Batch norm looks like we have n samples, and this one corresponds to one image. So each image becomes HYW by C because we have RGB channels. And you can see the colors here. And N by HYW by C becomes 111 by C. And layer norm becomes N by 111. You just need to see the color. And for instance norm and group norm, and I told you that group norm is the generalization of layer norm and instance norm. So when G equals 1, it is equivalent to layer norm. And when G equals C, it becomes instance norm. Okay, up to this point, we have discussed batch normalization. Think about this question on your own, and let's check the answer together. Okay, let's check the answer together. The answer is the first one. Batch normalization makes the training procedure robust to several hyperparameters such as learning rate. And batch normalization maintains the same behavior during training and testing. No, we need to calculate mean and variance in a different way for testing.